Hi, everyone. I would like to clarify a few things based on some questions that I got at office hours. And second, I would like to present one more little topic, and then we may as well start quantum mechanics tomorrow, so we start on a new day. Okay? So some clarifications. Sometimes students feel that homework or quiz or exam has nothing to do with lectures. And the reason that they feel it's not, well, first of all, that happens not because we do it on purpose. Sometimes it happens perhaps because the students are maybe missing the trees for the forest sometimes, and it's not, I'm not blaming you, it's not your fault, but that's why I'm doing this clarification. So there are two things, the last couple of lectures from last week, two takeaway points, okay. Take away points from lecture, what is it, 11 and 12. A, to solve problems, you just need to know the formulas, you can say, you can call it formula, for relativistic energy and relativistic momentum. E equals mc squared, gamma mc squared, okay? And the gamma includes the velocity, and this is the total energy, which is internal plus energy of motion. Also known as kinetic energy. Now, internal includes everything internal. It includes the mass energy, and one of the big ideas was that mass is really a form of energy. And it includes all the internal interaction energies. Okay? Maybe it did not get through in your mechanics class that potential energy is an energy of interaction. There's no such thing as potential energy of this, gravitational potential energy of this pencil. It's a gravitational potential energy of the pencil Earth system. It's the cost, it's the energetic cost of interacting with the Earth by means of gravity. So the potential energy is a form of an energy that's internal to the pencil Earth system. So this includes interaction potential energy and mass energy. Okay, mass energy is a new concept. Interaction potential energy is not a new concept. Maybe you didn't think of potential energy as kind of a energy of interaction that's internal to the system, but that's what it is. And in the light of relativity, that picture is crucial. You think of it as an interaction. In any case, here's your formula. You can use it to solve problems. But before you do that, there is also something called relativistic momentum. It's a vector, a regular 3-component relativistic momentum, equals gamma mu. The mu is the non-relativistic momentum, u is the velocity of the particle. And gamma mu is the relativistic. So you get a correction by a factor of gamma, which becomes a very big correction when speed approaches the speed of light. Notice both of these quantities are in a particular reference frame. We're not talking about viewing the same thing from different frames. I will say a word about that in a moment. And really, to solve problems, you actually just need these, you can call them formulas. So for example, this week, you will have a few problems in which you have to use these expressions. And so to solve those problems, you just need this, this information right here. So I'll give you an example. So for example, problem 88. Let me see if I can pull that up. Let me see if I can just for myself. I have too many. Okay, so problem 88 reads the following. I'm just going to read it out loud. A particle of mass m naught moves through the lab at 60% the speed of light. Okay, particle moves through the lab. What's the big deal? Suddenly, it explodes into two fragments. Fragment 1 has mass 0.66 m naught, 66% of the original mass, and it moves at 0.8 c in the same direction as the original particle. And then you're asked to determine the velocity, both magnitude and direction of, and the mass of fragment 2, right? So example, so this is 2.88, will be one of your homework problems. So you have inertial, you have a particle that's just sort of moving about. It has a velocity equals 0.6 c, and it has a mass m naught. And then the final, there are two fragments. Okay, one of the fragments we given information about 0.66 m naught, and u equals 0.8 c. You need to find this mass and this. So let's call it this. This is u naught. This is called u1, and this is called u2. Maybe u2 points to the left. Maybe it points to the right. It could be either, because you just know that the momentum vector has to be conserved, but you know, this is an awfully larger velocity, so maybe it depends. So we need to find these things. As always, in situations like this, whenever you solve problems of this sort, whether it's physics 141 or at this level, you just have to count the number of unknowns. So what are the unknowns, right? So the unknowns is m and u2. So two unknowns. Therefore, you need two equations. Here's the brouhaha. If you ask for mass and you only took phys 141, the answer is obvious. It's 0.34 m naught, because mass has to be conserved. Boom, we're done. We're done with mass. And then you just need one equation. Hopefully you understand from phys 1 that it's the momentum equation that we need to conserve momentum. The sum of m times v initial equals the sum of m times v final. Solve for the unknown velocity, you're done. But you see, mass is not conserved anymore. It's the total energy that's conserved, which includes mass energy. But as always, the different forms of energy can be transferred from one to the other. So mass energy doesn't have to be conserved, right? So it's the total energy that has to be conserved. So you see, because energy and momentum have to be conserved together. Okay, they always have to be conserved together. You can't just conserve momentum, you also have to conserve energy. So you have now two unknowns, because mass is not conserved. And the other unknown is the velocity, that's the obvious unknown. And so you need two equations, and the two equations are simultaneous conservation of mass, of energy and momentum. I hope I didn't miss. Okay, so again, now you have two unknowns, you need two equations, and well, lo and behold, the two equations are simultaneous conservation of energy and momentum, total energy and total momentum. In regular physics, you would think of this as only a one unknown problem, u, and you would only use one equation, the conservation of momentum, or maybe conservation of energy, but not both. Okay, the rest is plug and check, right? So set P initial, let me write it differently. Set P total initial equals P total final. In one dimension, I'm not putting arrows over letters, and this is relativistic, right? So this is a relativistic momentum. Like we're doing grown-up stuff. And second is you set E total initial equals E total final. Two equations, two unknowns, plug, chug, solve for M and U2. The rest is just math. might be a little bit tedious, and maybe your craftsmanship of how you manipulate equations. But that's just up to you. And so on. You have, I think, 4 problems that involve playing this game. Okay? So this is concreteness for you, concreteness that you might desire after having heard the last 2 lectures. Now let's go back to the last 2 lectures. I hope you would be able to appreciate that relativity makes things simpler. Less intuitive, yes, that's true. I give it to you. It's less intuitive, but it's simpler. So here's what I mean. You see, we started with this idea that space and time, I was going to do it in 1 spatial dimension. It's 1 single object called space-time. Okay, so when you go from 1 frame to another, you're intermixing. What's element of time and element of space in 1 frame becomes a mixture of the 2, and that becomes the time in the other frame. And what's element of space and time in 1 frame, that's a mixture of the 2, becomes element of space in another frame. So you have mixing. But while you have this mixing going on, there is one thing that remains the same, and that's the invariant. Okay, and that's the invariant, this quantity. Okay. Now this thing is like a position in space-time. Space-time is a space of events, and this is a position in that space of events. Well, you take a derivative, you get your velocity, derivative with respect to the proper time. Like a very natural extension of regular mechanics. You multiply by the rest mass, you get your form momentum, and you arrive to a derived quantity that turns out to have the meaning of basically energy and the relativistic momentum. This comes directly from this. And so some call it momenergy. Again, it's a single object. Momentum and energy are now bound together in pair forever. And so if you want to conserve the form momentum, although I just wrote the 2 components here, if you want to conserve the form momentum, like this, that includes all the spatial dimensions. Well, you have to conserve them together. Boom, right there. You can see where the conservation of both energy and momentum come from, because it's part of the same object. And there is an invariant again, which is minus E over C squared plus P squared. And you can also multiply it by a constant such as C squared, and that's still an invariant. So that's the story. So this idea that we interpret this component of the form momentum as energy and this component as the momentum was motivated. Okay, you might say, I don't care about that, just give me the formulas. Fine, I did give you the formulas. But I want you to appreciate the sort of the unified picture here, that this comes from this. And then it was a matter of interpretation that this reduces to mc squared plus the regular kinetic energy. So this must be the energy. And this reduces to the just mu at small velocities. So it must be the momentum. But really, the distinction between energy and momentum, it's a matter of, it's just a matter of language, because really in relativity, it's part of one and the whole object. So what we call energy and what we call momentum, it's not really fundamental, because when you switch to another frame, then what's energy in that other frame comes from mixing in of energy in the first frame and momentum in the first frame, just like space-time. Okay, and the other thing that we discussed is this concept of mass energy. Okay, so this is, let's see, so this is A. I gave you an example. I connected it to this general idea. And now the second concept is the concept of mass energy. Okay. So let me give another. Let me repeat. I gave you an example. Let me maybe make it clearer to get across the idea of mass energy. Although I think that you probably understood fairly well, but I want to reiterate this idea. It's not just that you can it's not just that you can blow up particles and convert them to light, right? And convert mass into other forms of energy, which is how nuclear energy works. But that energy sort of has inertia, right? And so again, let's say you have a positron. Now let's say you have an electron and another electron. What do you do to bring them together? What do you do to bring them together? Well, first you have to have breakfast. Breakfast is very important. Why? Because bringing them together costs energy. And where does that energy come from? It comes from you. Okay, so you take your hand. Okay, so this is your hand. Okay, and this is your other hand. Okay, and you force them. You force, apply external force to bring electron and electron together. Okay, you bring them together. You took some of your energy that you had from having breakfast, and where's that energy now? Well, we believe in the conservation of energy. That energy is now stored in the electric field that's between the electrons. You see, when the electrons were far apart, electric field had one pattern. When you force the electrons together, electric field pattern has changed. The energy came from you, okay, from having pasta, and now it's stored in the electric field. But just let that sink in, okay? The energy came from you. It was also stored in the electric field between the carbohydrate molecules, by the way. But anyway, now the energy is stored in the electric field between charges. Right? And let's say that now, okay, so you brought the charges together. Okay, antagonism, lots of energy packed in that electric field. And okay, so this is energy is stored in the new electric field. Not okay, electric field. Well, you know that if you release, that energy will be converted from this potential. Okay, so this is, by the way, potential energy. Okay, from this potential energy to kinetic. But let's say there's a latch. Let's say there's another electron. Let's say these are pieces of dust on which you place the electron. It doesn't matter. Let's say there's a latch. Okay, latch. So you bring, cling. Now they're together. Now you can let go. They're not gonna fly apart. Okay, there's all this energy stored in the electric field. Okay, so this is a latch, and this is energy, and energy stored in the E field. So what's the big picture? The big picture is you started with one configuration of particles and you ended up with a different configuration of particles that have energy stored in it. Okay, this is like your doublet. Okay, so doublet or a dimer. It's like your artificial atom. It shouldn't exist. You cannot have an atom with two electrons. You need an electron and a proton for them to attract, but you took care of that by having a latch. Well, there's energy stored in this atom. It's stored in space between them. It's stored in the electric field. So this mass of this dimer is bigger than 2 mass of the electron. You see, that's the brouhaha. Energy contributes to mass. And mass also contributes to energy, right? You can convert mass to other forms of energy. So we think of mass as just a form of energy. It's really weird. I'm a form of energy. No, but here's the again, you see, here's the fundamental, here's the deep stuff, really deep stuff. MC squared accounts for all the forms of energy, including kinetic, mass energy, and all the internal energy. I don't have to know about the physics of E and M. MC squared knows about that internal energy. That's incredibly deep. Okay. I don't have to know E and M. And I would want you to appreciate the idea that this really fundamental prediction that you can calculate internal energy without having to know the physics of how that internal energy is stored, that's mind-blowing. And the reason that this became possible is because we re-examined the very basics of the arena on which all processes take, the space and time. Now, so you see, I'm kind of trying to switch back and forth between applied, how to solve problems, and the big picture of what it means. One other thing about this mass energy. Notice that this dimer or doublet, it's composed of 2 internal particles, the 2 electrons. And so if you had a doublet that's far apart, and you end up with a dimer or a doublet, far apart. So think of this as a composite particle. And that composite particle changed state. Well, the inertia of this composite particle has changed. So if I hit this dimer with the foot, my foot will hurt more than if I hit this dimer with the foot, okay? But what I want to get across is if you have a fundamental particle like an electron that we don't believe has an inner structure to it, then you cannot change the rest mass of an electron. Okay? There is nothing inside the electron that you can pack energy into. In this artificial particle, the 2 electron dimer, it has an internal degree of freedom, namely the distance between them, that can soak up the energy. Okay, it's stored in electric fields, but the point is that there is a degree of freedom there, the distance between the particles. It's a composite particle. But if you have a truly fundamental particle, the one that does not have an internal structure, then there's nothing, you can't change its mass. So mass of a fundamental particle is its intrinsic property, like its spin or like its charge. On the other hand, composite particles like protons, neutrons, atoms, molecules, they have an internal structure. Therefore, by changing that structure, by changing the configuration, perhaps cis to trans, or from one state of an atom to an excited state of an atom, and so on, you are actually changing the inertia of that component. So I think I said that, but maybe it went really quickly last time. Okay, folks, I am trying to keep a good balance between applied and fundamental. So that's what I wanted to say. I hope this clarifies lecture 11, and especially lecture 12. I gave you kind of hints for what you have to do to solve a few problems that will appear on this week related to the previous week. And now in part 2, I will say just a bit more about relativity, about kinetic energy and dynamics, and then that would be it. Okay? So I'll see you in part 2. Thank you.